Hi, this is an example problem from section 3.4, relative velocity in 2D. We're going to go ahead and solve this problem using the mathematics of vectors, but the process is the same as we saw previously in the 1D example. So read this for a moment and understand what we're looking for. Okay, we're going to try to, we're asked, what is the velocity VBG of the boat relative to the ground? So we're looking for this. Velocity of the boat relative to the ground. It's always good to be familiar with your three reference frames that are considered in this problem. So we know we've got the boat, we've got the ground or the shore, and then we've got the water itself. And we've been given the velocity of the boat relative to the water here, and that's been drawn out right here. Similarly, we've been given the velocity of the water relative to the ground, right? So we do know these two vectors. We do know velocity of boat relative to water. So that's, you can think of this as if you're floating in a raft on the water and you look at the boat, you would be measuring the velocity of the boat with respect to someone that's moving with the water. We also know the velocity of the water with respect to the ground. And that's the velocity that you see the river flowing if you're someone standing on the ground and you measure the velocity of the water flowing. Now we're going to go ahead and use the little method we use, that trick to remember how to write the vector equation. So what's the third reference frame that we haven't used here in this one that we're solving for? It's the water, right? So I'm going to write it like this. It's going to be VB, I put water in next, and then I put water in first, and then I write it like this. Okay, cool. Check. Are these two things the same as these? It looks like no. Or no, never mind. We are good. Yeah, these match up. BW, BW, WG, WG. So we don't need to make any more changes there. All right, clean this up a little bit here. So the important thing here is that this is a vector equation, right? So we're going to have to use vector addition to do this one. Now, for a vector equation, remember, a single vector equation here, it's the same as two equations, one for the x direction, one for the y direction. So all we need to do is figure out the x and y components of our vectors and do vector addition, and we'll be able to solve this problem. Again, to do that, we want to go ahead and plot our vectors and be able to figure those out. So let's go ahead and just create a little space here. I'll go ahead and draw some coordinate systems to set that. So here's our coordinate systems, and lucky these are the simple vectors that are aligned parallel to one or the other coordinate axes. So for V of the boat with respect to the water, and you can kind of see it plotted here, right? It points due north. So all of the magnitude of that vector, all 4 meters per second, that's in the direction north, right? How do we figure out the components of that? Well, let's go ahead and make a little chart here. All right, so we've got our table, and for the velocity of the boat with respect to water, we can see that here it's got 0x component, and all the magnitude therefore goes in the positive y direction. Now let's go ahead and look at the velocity of the water with respect to the ground. There you can see it plotted there. And so if we draw that vector here, it's due east, and it has a length of 2 meters per second. So all the magnitude there, the length of the arrow, is in the eastern direction. When we go ahead and write this into our table, that means that the y component is 0 and the x component is positive 2 meters per second. Now to figure out what is the velocity of the boat with respect to the ground, well, we're just going to go ahead and do vector addition here, right? So we're going to go ahead and add these two guys right here. And so we got to add x's with x's, so 0 plus 2 meters per second gives us a 2 meters per second. For y, 4 plus 0 meters per second gives us a plus 4 meters per second. And in fact, they've actually even plotted that vector here. You can see it is in the first quadrant, so it's plus plus. That's good. And if we actually do our vector addition the way that you do it from a start point, then put the second vector here from tail, draw, and then you can see that we end up getting from the start to the end, we draw our vector. There's our graphical vector addition. Works out great. Now, it says, what is the velocity of the boat relative to the ground? Well, this could be our answer here if we want to give the two vector components. If we want the speed, of course, we need to do the Pythagorean theorem. And so this says express VBG as a magnitude and directional angle with respect to due east. That means magnitude, speed, right? So we actually aren't going to use this as the answer because they told us to do it in a different way. So to calculate the speed here, Pythagorean theorem, the speed of the boat with respect to the ground, that's equal to the Pythagorean theorem, where we're going to take the x and y components and square them and add them and then take the square root. And so let's go ahead and put those numbers in. And so we get 4.47 meters per second when we put these numbers into our calculator. Now to get the directional angle with respect to due east, we should go ahead and plot our vector and then figure out the angle. So let's plot the vector here. So I've produced a nice XY coordinate system. Let's plot our vector here of the velocity of the boat with respect to the ground. We know it looks kind of like this. And in fact, we already know what the x component is, right? It's equal to 2 meters per second. And we know what the y component is. It's equal to 4 meters per second. And what we're trying to do is figure out an angle here, theta. So we want to start east and then move by an amount theta towards the north, right? So what is that angle? Well, let's go ahead and use our trigonometry to do that. So that angle theta is going to be equal to the inverse tangent of the opposite side of the angle, 4, divided by the adjacent side, 2. And when we put that into our calculator, we get an answer here, 63.5 degrees. And how do we say that now? So it means that we're going to start here in the east direction, right? So write that last. And then we're going to move how far? 63 degrees toward which direction? We're moving towards the north as we go up, right? So this is going to be 65 degrees north of east. And there we've got our direction with respect to due east as a cardinal direction.